Good morning and welcome to everybody in Galletti. My name is Michele Galletti. I'm Managing Director of the company. I'm together with Enrico and Michele, our export manager. And today is a very important day and a special day because today together with us there are also Adab and Daryl from HVAC Specialty, one of our best partners in the world. So I'm very happy now to ask them to join us and to start the presentation. Thank you.
Thank you. Thank you very much, Enrico.
Hello.
Michele. Thank you.
Thank you.
All right.
Thank you. Thank you. Thank you. Thank you. Good afternoon, everyone. Daryl Clark here, Chief Operating Officer with HVAC Specialty. I cannot tell you how excited and thrilled I am to be back here in Italy, just outside of Bologna at the Galletti World Headquarters. This is an amazing partnership between HVAC Specialty and Galletti. Today we have Bob Barrett doing a presentation for you comparing C02 heat pump technology versus R454B heat pump technology for domestic hot water heating applications. Again, we are excited to be here. An amazing partnership between HVAC Specialty and Galletti. And here to tell you more about that, my colleague and Vice President, Mr. Adam Hirsch.
Thank you, Dale. Appreciate you.
Yes.
All right. So everyone, it's very exciting to be here in Bologna, Italy at the Galletti factory. For those of you who are joining us for the first time, Galletti is a 118-year-old company that for all those years has been delivering high-quality, innovative, energy-efficient products. Today, the company is run by the fourth generation of the Galletti family, with the fifth generation working here. They are a proud family and a proud organization that delivers modular heat pump chillers for heating, cooling, and domestic hot water around the world. Today, they are a leading manufacturer with today's refrigerant, a 410A, 454B, which is being circulated across North America, United States, and Canada right now as we speak, and throughout Europe and the rest of the world, implementing heat pump chillers with R290 refrigerant, that's propane. R290 refrigerant, which we're a couple of years away from delivering into the North America market. And when that's ready and the EPA approves it, we'll be ready to deliver that technology and future modular heat pump chillers to the market. Galletti is highly focused as an advanced design company. What does advanced design mean? It means bringing tomorrow's technology here today. But besides being a company that focuses on high quality, innovative products, it also prides itself on delivering technological solutions to the local market. It provides engineering support to consulting engineers, developers, contractors, wholesale distributors to ensure that each and every project goes off as expected at installation and well into its operating life. And to ensure that it meets North American needs, it has a headquarters in the New York, New Jersey market with local representation throughout each 50 states. So wherever your project is, whatever your building type is, there is a local Galletti North American sales representative organization that has expertise in heat pump technology as well as hydronic solutions. So one of the ways that Galletti does excel from its competition is ensuring that not only do our partners have expertise in heat pumps, but how that heat pump ties into the building. How does it tie into the plate and frame heat exchangers, the circulators, the expansion tanks, to deliver the heating, cooling, and domestic hot water solutions? So we We're excited to have you with us today. Coming on next is Bob Barrett, one of our senior engineers in our Building Solutions group. So with that, Bob Barrett.
All right. Thank you, Adam. I guess we'll get into it. So today's presentation is going to be evaluating the performance and cost comparison between air source heat pump, domestic hot water plants using R454B refrigerant and C02, R744 refrigerant. All right, so we'll go through the outline here quickly. So what makes CO2 refrigerant attractive? How does CO2 compare to R454B? We'll talk about temperature as it relates to lime and scale buildup. We'll talk about temperature as it relates to health concerns. And we'll talk about temperature as it relates to safety of the occupants of the building. Also, we'll talk about operating delta T's and energy balance, operating profiles of buildings and commercial settings, the operating delta T and the air source heat pump schematics. So we'll compare CO2 and how they typically apply their technology to domestic water. And we'll also compare R454B with a few different schematics as well. We're also going to compare the equipment efficiency of CO2 versus R454B equipment and the system efficiency of CO2. Now, the CO2 system uses a slightly different way of dealing with the recirculation, so you have to factor in that, and we'll compare those as well. We're also going to compare the global warming potential of the two. A lot of confusion on that, and then we'll get to the conclusions. So, all right, so what makes CO2 refrigerant attractive? I think a lot of people initially, especially on paper, CO2 seems like kind of a wonder refrigerant in comparison to other ones. So we're going to kind of talk about that first, and then we're going to talk about maybe where it isn't. So CO2 has a GWP of 1, and that means it has a global warming potential of 1. So CO2 is a gas that contributes to global warming. I think we've all heard about that. But given the high global warming potential of refrigerants like 410A and 134A, CO2 is a useful benchmark to compare them against. That's why it has a rating of 1. CO2 also has high discharge temperatures, so it has leaving water temperatures of 175 up to 174, which is in the range of traditional HVAC equipment, and it's hot enough to provide immediate disinfection of most bacterial concerns that people have. And it also, can operate down to relatively low ambient, so it'll go down to negative 13 degrees Fahrenheit. At least that's where it's rated. Probably operate below that, as will most equipment. But the rating, test labs are only so extreme, I guess. And then it also has a reasonably high efficiency. So it has a COP of 3.65. That was just pulled from one of our competitors' data. And that's at a leaving water temperature of 149 degrees Fahrenheit, with an assumption of 60 degrees Fahrenheit entering water at an ambient of 44 degrees, which is a pretty good mean seasonal average temperature in the winter between zones 4 and 5 in the US. So let's take a look at this comparison. On the left, we've got our CO2 unit. On the right, we've got our Galletti R454B unit. So as we mentioned before, the max temperature of CO2 is about 194. Our Galletti unit tops out with R454B around 148 degrees Fahrenheit. Now, the typical delta T that a CO2 piece of equipment wants to operate at is between 70 degrees and 90, which is a pretty high delta T. The delta T of the Galletti units is a more typical 10 to 14 degrees. If we're talking water heaters, most gas-fired equipment typically runs around 20 to 25 and relies on sort of a multi-pass configuration. Now, the minimum delta T that a CO2 unit can operate at is 45 degrees Fahrenheit. Again, a relatively large delta T, whereas we can operate the R454B unit with as low as a 3-degree differential between supply and return. The refrigerant pressures on CO2 is quite high. It's 1,500 to 1,800 PSI. So you need some pretty beefy components for that kind of pressure. And also the technicians that are rated to work on that is definitely a smaller pool. The Galletti units are a more typical refrigerant pressure of 300 to 550 PSI. And then the minimum rated temperature for CO2, as mentioned before, is negative 13 degrees Fahrenheit. It actually starts to derate off of its max temperature capabilities around 27 degrees Fahrenheit. So you don't get the same sort of high level temperature at 27, it starts to go down. Whereas the R454B units are rated to -4. and the D rate starts around 12 degrees ambient. So you can get into much lower temperatures before you start to lose your max temp capability. And again, those min temperatures, I think people get concerned about that. That's just what these things are rated down to, and that's a function of the test chambers. So the units will both likely probably operate below that, but you get into a less stable range at a certain point. All right. Looking at some other comparisons, so the piping configuration on CO2 tends to be what's referred to as single pass, and I've got some schematics a little later, so we'll get into that. Whereas the 454B is a multi-pass unit, which is a more traditional kind of piping arrangement, similar to what you'd see with like a gas-fired piece of equipment. As I mentioned, the piping layout for 454B is traditional, where CO2 isn't. Also, CO2 equipment is not able to service the building domestic hot water load directly. They use what's referred to as a swing tank, which is the electric resistance heater to deal with domestic hot water recirc loads, whereas the 454B equipment can handle the domestic hot water recirc loads. And then there's also this concept of hybrid plants where you integrate gas-fired equipment with air source heat pump equipment. And the reasons for doing that are many. You might want to do it for redundancy's sake. You might do it for resiliency if you're in an extreme weather environment, if you will. And also if you don't want to, deal with the larger D rates at extreme cold temperatures, if you're in a very northern climate. And, if you have existing gas infrastructure, there's a whole bunch of reasons to do that. It's relatively tricky to do with CO2. It's quite easy with 454B. So we'll get into all of these things. And then the other thing is financial consideration. So the first cost of a CO2 piece of equipment is roughly 2 times the cost of a 454B unit. That's kind of anecdotal. We're sort of getting ideas of where the competition is at the moment. Maintenance cost tends to be quite a bit higher as well, partially because it runs at such high pressures that the components are, pretty heavy duty. And again, technician labor and stuff is pretty limited. So all those things kind of drive up cost. The CO2 equipment tends to be more complex as well, whereas the 454B unit is more of a traditional kind of setup. And then the equipment efficiency, as far as the ratings go, tend to be higher with CO2 if you compare it at a given ambient temperature and delta T. But that said, the 454B units are still quite high. But when you compare the entire plant efficiency, CO2 equipment tends to be lower, and that's what we're going to get into today, because I don't think that's necessarily intuitive for a lot of people. And we end up being higher on the 454B side. From a sound standpoint, I would say that the CO2 is sort of normal to high, whereas the Galletti units are sort of in the normal to low range. So let's keep going. So temperature and lime scale production are just lime is just a fact of nature when you're dealing with potable water. So lime scale is a common problem in domestic water systems. It's mostly comprised of calcium carbonate, and the lime is dissolved basically in the water. So when you heat it up, it comes out of solution. It tends to come out kind of like a wet clay. And that lime is sticky, and it'll stick to the heat exchanger surface, especially if it's at low velocity. And if you keep heating it up, it becomes hard like a rock. So here's a picture of a gas-fired water heater that was cut open. This one failed before the warranty period of 3 years. And you can see inside of it, it looks like there's gravel, like rusty gravel inside the bottom of it. Now that, didn't come from the water line per se, right? It didn't come in as hard rock. It came in dissolved in water. And when you heat up water, especially if it's in a low velocity area, it settles down to the bottom. And in this case, there's a concaved, I guess, or convexed, heating element where you've got fire underneath it, and it heats up the water. Well, when the lime precipitates down, it forms a hard, thin layer of rock, basically. And then through heating, and if the water gets trapped below it, right, it'll create little pockets of steam, or it'll just expand and it breaks. So you end up with this kind of gravel at the bottom of your heat exchanger. Now this chart shows, and I'm not sure what the hardness of this water is per se, but it gives you an idea of how lime deposits as a function of temperature and as a function of volume of water. So in this example here, let's say we have 100 people living in an apartment complex. Maybe it's 50 apartments, and each person consumes 30 gallons per day of water. So that would be about 3,000 gallons per day. So if you're generating hot water at 180 degrees off of your domestic water heater, you're going to produce, what's going to come out of solution, right, is about 150 pounds of lime per year. That's, the weight of a decent sized human being, right? Now, if you, in that same water quality, if you generate at a lower temperature, you can cut the lime production in half at 140. Okay, so instead of 150, we're at about 75 in that regard. And if you generate even lower still, now you cut it into about a third, and we're operating around, I don't know, 45 or 50 in that range. So, and this translates, the harder the water, the more lime, the less hard the water, the less lime. But obviously, the higher the temperature, the more lime comes out of solution. All right. So there's also some health considerations when it comes to the temperature of the water. And basically, we hear Legionella a lot in the US, especially all these Legionella concerns with domestic water. And I did a little digging into the data on this, so I want to share it with you. So if you talk to some people, they consider it a real health concern, and it's a major issue that we have to address immediately. I think it's actually more of a moral panic, but I'll show you some data and you can make up your own mind. So Legionella is a bacteria that can infect and replicate within the lungs. This can result in Legionella's disease, which is like a pneumonia, or the less severe Pontiac fever, which is more like a mild flu. Both kind of have flu-like symptoms in the beginning. Legionella transmission is via inhalation of water drops from a contaminated source that has allowed the organism to grow and spread. Cooling towers are a good example, right? They just draw in a lot of air. There's a whole bunch of sites for it to live. If the chemical treatment isn't great, right? It's got a lot of places to live. Now, the CDC data, this is a summary of 14 years of CDC data from 2001 to 2014. Up here, we've got all of the cases that resulted in some sort of sickness. So this doesn't have to be extreme sickness. It could be the milder form of sickness. So in 14 years, there's only been 402 people that have contracted Legionella and been brought to the hospital. Out of those, right, we've got 312 that are confirmed, 90 suspected, so they weren't actually, documented per se. And then the deaths associated with it are 65. Now, this is over 14 years. This is all cases. The cases related to potable water as an average per year is 1.8. Now, this is out of 600 million people. This is all of North America, okay? The ones that were associated with potable water are in white, but how they associated it, very poorly sort of noted in the data. Now, just to give you some reference, because everyone's bad with their intuitions on statistics, the number of deaths due to lightning strikes worldwide per year is about 4,000. Now, there are about 8 billion people walking the planet, so you have a 0.00005 chance of being killed by lightning. According to the CDC data in North America, you have a 0.0000003 chance of dying due to Legionella caused by plumbing systems. So you're 166 times more likely to die from a lightning strike than to die from contracting Legionella from a plumbing system. Now, within that data, it should be noted that the majority of deaths are people, 85% by the way, are people 50 years old or older that have compromised health systems. And of that 80% of them are 85 or older. So again, as far as like most people walking around, your odds of dying from Legionella in the plumbing system is basically nothing, okay? All right, so that out of the way, let's talk about temperature and safety. So this is just different charts. The temperatures are slightly different, but they more or less agree. There's some slight variation. I think it's a result of if they're considering scalding at a 3rd degree, 2nd degree, or 1st degree burn. Basically, 165 to 175 is what's considered disinfection range. When we talk about pasteurized milk, they bring the milk up to about 160, 170 degrees, and then they cool it back down. They don't boil it, right? So that's enough to kill the bacteria that most people are concerned about ingesting. 140 degrees is dangerous. You will burn yourself quickly at 140 degrees. And that is why code in the US anyways dictates that you can't distribute water hotter than 120. So 120 is considered safe for distribution. I think every residential domestic hot water heater in the world is set to about 120 degrees. So usually residential domestic water systems don't have mixing valves. They don't have domestic recirc systems. And so they set them to 120 because that's a safe temperature to store the water and not burn people. 110 to 115 is the distribution temperature for nursing homes and some childcare facilities. Again, they want the temperature lower because people are a little less spry. They can't get out of the way of hot water. And then most people shower with about 95 degree to 105 degree water. Really, 110 would be the hottest shower you're ever going to take. And 100 degrees Fahrenheit is considered safe for bathing, okay? Now, if the water temperature is at the shower is 105 plus or minus, everyone in the building is going to be happy. They're not going to notice that anything has changed in their system. All right, so let's continue this conversation. So maintaining 140 at all times in the domestic hot water heater is not necessary for safety or for human health, really. The tank temperature of 140 is actually a legacy of non-condensing water heaters. So basically, non-condensing water heaters would condense around 135 degrees Fahrenheit, which is why historically we have stored temperature at 140 in domestic water systems. The antibacterial benefits of 140 storage are effectively solving a non-issue. It's kind of like selling caffeine-free water, right? You know, water doesn't have caffeine in it, so not really an issue. Now, the Galletti HTH series units will produce 148 degree water down to 12 degrees ambient. So that's pretty warm temperature water down to pretty cold temperature outside. And we can produce 140 degree down to 5, which again is extremely cold because freezing is 32 degrees Fahrenheit. And we'll produce 131 degrees down to -4. So 131 is 11 degrees above the 120 degree distribution temperature required by code. And the tank temperature of 140 is achievable down to 10 degrees Fahrenheit with a 5 degree approach with an indirect domestic hot water heater. Now, just again to know, every residential domestic hot water heater is set to 120 or lower. So again, 120 degrees is plenty safe. So I want to talk a little bit about how domestic water comes into the system and the temperatures that we typically see in a domestic hot water system. So cold water out of the ground in winter might get as low as 40 degrees. Generally speaking, in a commercial building, it's never 40, right? Or very, very rarely. It's usually 50, 60, sometimes as high as 75. It really depends on how far away your plant is from the ground source and what the temperature is outside even. So even in winter, you can have a 70 degree entering water temperature if you're on the 15th floor of a building and the cold water takes time to get up the stack. It just comes up to ambient temperatures. Now, by code, we have to distribute at 120 degrees out to the building. So our domestic water recirc is usually going to come back around 115 to 110 degrees. An appropriately sized pump with an appropriately balanced system will usually give you a 10 degree delta T. My experience has been when I do domestic water flow studies is the pumps are always oversized and they're never balanced. So typically the delta T's are quite a bit smaller. So when the cold water and the hot water blend, you typically get a temperature somewhere between 80 and 115 degrees. And that's just steady state most of the time, the coldest temperature you're going to get, okay, back to your domestic storage tank. So your domestic storage tank is going to be stored, let's say commercially at 140. It might be stored at 120 residentially. And again, one of the reasons we store at higher temperatures sometimes too is it gives you effectively more capacity for a smaller storage tank. So that's another reason you might jack up the temperature. It kind of allows you to shrink down your tank a bit. But basically that colder water comes in, and even if it's at 40 degrees and you're storing at 140, it's going to immediately come about 90 degrees, right? Because it's going to blend instantaneously as soon as it hits. So what ends up happening is you have 90 to 100 degree water kind of in the bottom of your tank. And then you've got roughly 120 to 140, depending on the application, right at the top of your tank. Now, the flow rate, let's say the cold water's coming in at X GPM, right? We don't know what it is, it varies. Typically what's going to happen is, and this again is just a gas-fired unit, for example, we've got about 3 to 5 times whatever this flow rate is over here. And the reason that's done is typically water heaters are sized with about 20 to 25 degree delta T. They do that mainly because it kind of matches what boilers are sized for, right? And it typically similar products, just different materials. Also, they do it to prevent limescale buildup. So one way you can prevent limescale buildup is to have a heat exchanger with a reasonably high velocity. So the way these tanks work is the tanks, the pump and this water heater stay off when the tank is satisfied. but when it becomes unsatisfied, what happens is this pump kicks on, and basically it's going to draw water through quickly. If lime gets precipitated out, which it will, it's still kind of like a wet lime scale, and it flushes out. It goes to the bottom of the tank where it doesn't get refired. It just settles out in the low velocity area where you can drain it out, right? It doesn't cause any harm. Now, as we come in, there's some mixing that goes on in the bottom of the tank. The top is sort of stratified, right? There's usually a baffle in here as well to kind of prevent some mixing of the top part of the tank. And as long as the BTUs here match the BTUs here, you're good, right? And even though this is multi-pass and you might take 3 or 5 passes to, get to the delta T you want, this is a very short distance. This water's moving very quickly, and it's essentially an instantaneous heater if the capacities match, right? So I think people get hung up on this multi-pass thing, thinking it's like an HVAC loop and it goes out 1,000 feet and comes back 1,000 feet. It's moving, 25 feet away or 50 feet away at 5 feet a second or higher, happens pretty quick. So, people can get focused on flow, they can get focused on delta T, but basically when you're reviewing an energy balance, if the energy in equals the energy out, all good, right? So let's take a look at this. So we got 10 GPM coming in on cold water flow, and we're going to have 100-degree delta T. Again, it's never 100-degree delta T, but a lot of engineers will assume 40 coming in, 140 going out, because you're storing at 140, and 40 is the worst case scenario. So this is, a delta T at a certain amount of gallons, right, is a BTU. So it's a statement of energy. If you give it a time frame, it's a statement of power. So we can balance this out, and we said that we're going to do a 20-degree delta T on this side. So we need 5 times the flow rate on this side at a 20-degree delta T to match 100-degree delta T at 10 GPM, all right? So a couple notes on this, right? The real delta T that a water sees typically is somewhere between 30 and 50-degree delta T, right? It's coming in around 80. We're heating up to like 120. That's a 40-degree delta T in terms of what you need to do to keep up with the capacity. Now, in an off-peak situation, you might, store hotter water or whatever, but if you're just trying to hit peak demand, 40 to 50-degree delta T is pretty common. Traditional gas-fired water heaters typically, like I said, operate with 20 to 25 per pass. Time for a pass is extremely short, right? So if your BTUs can match the BTUs of your load in an instantaneous fashion, you basically have an instantaneous water heater, even though it takes a few passes to get there. Small delta T's result in higher velocities, which is good for the heat exchanger and for heat transfer. And it's a useful way of mitigating lime scale buildup in your heat exchangers. And domestic water flows on average exceed the makeup water flows most of the day. So the resulting cold water entering temperature is actually warmer than most people assume. So, these large peak demands for cold water occur very rarely, a couple hours a day. The majority of the day, the domestic water recirc is running 24/7. Now, one thing to note, there are some energy codes that are sort of in conflict with manufacturer recommendations. So, the domestic water recirc really only needs to run between like midnight and 6 in the morning. It can stay off the rest of the day because the rest of the day, there's usually enough domestic water to keep the pipes warm. The problem is if you store your tank at anything over 120, you're going to need a mixing valve for code reasons and for safety. And as soon as you put the mixing valve in there, you have to run your pump 24/7. Because if you stop the pump, what's going to happen is this valve's going to hunt itself to death. And these are pretty expensive. So when you got the valve, this is running 24/7. When this is running 24/7, you're losing heat in your pipe, more heat than you would otherwise because you're running water through the piping more often. And so energy and safety sort of have a conflict here with these devices. All right. So this is real world data that I measured in a low-income housing in New York City. It had 163 apartments, and it looks extremely busy, so I'll walk you through it. So this was a steam heat exchanger, so you can see the water coming off the heat exchanger was quite hot. It was about 190 degrees, plus or minus a bit. It went through a mixing valve. The mixing valve knocked it down to about 125. It was reasonably consistent throughout the day. The domestic recirc was about 7 to 10 degrees off that temperature, which is actually a decent amount of flow for the load, and or it was reasonably well balanced. Down here, in brown, this is our entering temperature coming into the tank. And you can see here that that's a blend of domestic water recirc and cold water. And we never really dropped below about 90 degrees, right? Maybe high 80s, but we're up to 110. And our cold water coming in through the pipe was about 60 degrees, pretty consistent, okay? So even though this is 60, when you factor in the recirc, right, we're at about 90 to 100. Now the cold water is here in light blue, and it's over here as far as the GPM. So even in the middle of the night, there were things going on in this particular building. So that's a little bit surprising. And then the peaks you can see aren't very peaky, right? So from, 8 in the morning till about almost midnight, 11 o'clock, there was, a fair amount going on, but it didn't become like a high peak and then a low valley. It was just a series of sort of smaller peaks and valleys. This yellow line is the domestic recirc line. So you can see here, this is 17 GPM, and that's running 24/7, right? So our flow rate, the majority of the day, is above our peak cold water flow rate. And there's a few times where the peak water crested above it. We get to about 22 GPM or so. But again, that flow for the domestic water recirc is more flow. Looking at that a different way, here's a graph of the cold water makeup flow. Here is the domestic water recirc in orange, and then this is the total flow seen in the piping, which is a combination of the two. Couple things, the average number of showers per minute in an instantaneous fashion was roughly 4. So out of 163 apartments, about 4 showers were running in any one instant on average, or the equivalent of 4 showers worth of water was running in the system. Could have been sinks and other things, right? The peak number of showers per minute is only about 10%, which means with all these showers, 163 apartments, 163 showers, only 10 showers were running in any one 1-minute interval, okay? The domestic hot water recirc flow rate was 17 GPM. The peak cold water makeup flow rate was 21 GPM. The average makeup flow rate of the cold water was 8 GPM. So the average domestic hot water flow was twice the average cold water makeup in this building. The domestic water recirc load as a percent per day was 15% of the total load, okay? So that's because we've got a mixing valve that's running 24/7. Now in this particular building, the cold water demand was reasonably high most of the day. And that's what you find in a lot of lower income stuff. People don't follow the same sort of patterns. And so there's more people home throughout more of the day. There tend to be more people physically in a certain square footage when you have lower income, just because real estate's expensive. So the way you make it cheaper is you fill it with more people, right? Now, as far as the load goes, like load is not just flow, but it's flow at a delta T. The delta T on the domestic recirc is relatively low. The delta T on the cold water is quite a bit high. So the actual heat input load, like I said, is about 15% per day for the domestic recirc, whereas the cold was, significantly more. Now we're going to switch gears here and talk about a different application. This is high income, also in the New York City area, also multifamily. This said it was a bigger building. It's 388 apartments, and this was pre-COVID, right? So, this was more of a traditional schedule. So here we are with basically nothing happening on the cold water demand side throughout the midnight hours through about 5, 6 in the morning. Got a couple early risers, and then the majority of the people start coming in around 6, 6:37. With your peak about 7:30 at about 47 GPM. And then that continues to about maybe 9, 9:30, upwards to maybe 10, 11. And then there's not much going out throughout the day, but there's a few spikes here that are kind of high and sort of surprising. And then in the evening time, right, you've got another sort of peak load, but it's not as peaky, but it lasts longer, okay? So the average number of showers here, though, is 3.5% of the total. So on a 24-hour basis, pretty low, right? But very similar to our low-income housing. The number of showers per minute is 11% here, where before we were at 10% with the low income, right? So again, pretty consistent in terms of like instantaneous demands. Now you can see the peak is very different, right? So I could store a bunch of water here and have a much smaller water heater in the storage tank could, hit this peak, and then it has a nice valley to recover for the next peak. So if you're sizing equipment versus storage, the higher income gives you a little bit better benefit with storage because you have all this time where nothing's going on. You can store a bunch of water and then use that stored water during the peak. But in terms of like instantaneous sizing, it's not much different, okay? Now here's the other crazy thing in this building. This building had domestic hot water recircs that were flowing at 125 GPM, and that was by design. The engineer had designed it to flow 125 GPM, which is kind of crazy, and it was. So when I did the calculations initially, I put the flow meter on the leaving water side of the three-way valve, and that picked up the domestic hot water flow rate. So in the middle of the night, we were getting almost 150, 125 GPM. It kicked down lower during the day. You can see the peak, the morning peak. The evening peak's a little harder to detect in this thing because that 20 GPM looks smaller on this particular graph. But if we switch back, right, nothing from a cold water standpoint going on. Big peak in the morning, not much going on for the middle of the day, smaller peak. 47 GPM, roughly 20 to 15 over here. The data's still there, right? But that's the kind of crazy that you can see out in the world. Now, when you run through the numbers on this, even though the delta T was about 3 degrees, that's how much, delta T was being lost through this large 15, I think it was like a 20-story building or something like that. There was so much flow going that even at that low delta T, it was actually 150% of the load per day. So they were actually, the domestic load was, 1.5 times higher than the cold water demand per day, which is, again, kind of crazy, but in this example, it actually did happen. So, when you think about instantaneous domestic hot water heaters and how they're sized, they have to hit the peakiest peak and the peakiest delta T if they don't have storage. Now, with heat pump technology, we almost always want storage, right? But even with gas-fired equipment, there's this idea of like, let's go lower and lower in the storage because tanks are expensive and they take up a lot of room. They don't really run well if you don't have storage, though, okay? So it's good to look and see how the system actually operates and to think about how poorly instantaneous systems function, right? So just good to have data every now and then, just sharing. All right. So let's talk about operating delta T's with air source heat pumps. So we mentioned before that CO2 equipment runs with a pretty big delta T and that the R454B units run with smaller delta T. Now the problem with CO2, as we alluded to earlier, is that it cannot handle the domestic hot water recirc load of a building because it might operate with a 10-degree delta T at most, but usually it's 5 degrees or something lower. So the question is, how do you solve that problem if you're a CO2 producer? Well, you add a swing tank, right? And a swing tank is basically just an electric resistance heater that you're adding to your heat pump plant. So let's take a look and see what that looks like. So in this schematic, the blue line is cold water. The orange line here is, or yellow line is domestic recirc. And the red line is hot water coming off of your heat pump plant. So normally what happens is cold water makes hot water, right? So cold water comes in, pushes up through the tank, and it serpentines through this tank. Okay, so it's pushing out, and it makes the hot water, and then the hot water comes into the electric water heater, and then through the mixing valve. That's one path it can go. Now, the recirc can't take that path because it would warm up this tank too much, then this wouldn't work. So the recirc goes directly to the electric water heater. So the electric water heater is almost always on because it's always got a domestic load it has to satisfy, okay? Now, the cold water comes in, and with this, and what you'll see in domestic hot water tanks is they usually have a lot of storage. And the reason they have a lot of storage is they have to store cold water before they can kick on, and a fair amount of it too, because they want the unit to run at least 10 minutes. So they're going to have at least 10 minutes worth of cold storage, in these tanks, maybe more, right? And so in this example, this would probably all fill with cold water and maybe half of this before this heat pump kicked on. And then when this heat pump kicks on, that pump's going to draw that cold water back down the tank, right, into the heat exchanger, heat it up. Now it's a one-pass system, meaning it'll go from cold temperature of like 60 degrees up to like 150 degrees in one pass, right? 90-degree delta T. So we've got that 90-degree delta T coming out here. So now we're at 150. So now we're storing our tank at 150, maybe hotter, right? And we're going to backfeed until this whole thing is hot again, and then we'll shut off. So it's a, on for a while, off for a while kind of system. And then this hot water eventually, like I said, will feed out, right? If the cold water's pushing through, it's going to push the hot water out, right? Water's incompressible. So it's going to push that hot water out, push it into the, what's going on there? All right, cool. All right, so CO2 systems, like I said, require these large delta Ts. The CO2 domestic hot water tends to require larger storage tanks, in part due to needing that cold water demand, right? 100% of the building's domestic hot water load is going to be handled by the electric resistance heater, which has a COP of 1. And the domestic water recirc loads are typically between, typically 10% of the peak loads, but they could be 30 to 60% of the total load per day. All right. Now, when applying CO2-based domestic hot water equipment, you got to be assured to account for that. So we're going to account for that now. Yep. In a couple more slides, we're going to account for it. So let's compare that schematic with what we would recommend for Galletti equipment. So what you'll see here is you get your cold water unit coming through your PRV. It goes to the bottom of the tank. And you can see your domestic water recirc blends with the cold water, which is very typical for any kind of gas-fired equipment as well. So that blended cold water comes to the tank. It sort of stratifies on the bottom. When the tank, which is usually, or the tank thermostat, which is usually about a third of the way down, says, hey, I need to call for heat, what it's going to do is going to kick on these two pumps. It's going to kick on the air source heat pump, and it's going to circulate hot water from the air source heat pump through a double wall brazed plate heat exchanger. In this case, it's mounted on the outside of that storage tank here. And it's going to circulate cooler water from the bottom of the tank through the heat exchanger, blending it in on the bottom side here. So it keeps this hot. And then the hot water is stored on top, goes through the three-way mixing valve out to your system. Okay, so very traditional piping setup, really. Now, one thing we mentioned before is that you can integrate these heat pumps with a hybrid plant very easily. So on the left-hand side of our diagram here, nothing has changed. You can see here we got a glycol makeup unit. So if you're in a cold northern environment, you're probably going to have glycol in your system on the heat pump side because you've got hydronic components on the outside. If you're in a warmer environment, you might forego the glycol, but basically the left-hand side here is unchanged. So if the heat pump is keeping up with the load, you're going to have hot water leaving, and it's going to come into the cold water side of the storage tank. Now, if it's keeping up with the load, this just becomes additional storage. Gas-fired unit never kicks on, okay? If it's not keeping up with the load, let's say the load drops below what the set point on the secondary tank is, then the gas-fired piece of equipment comes on, and it, tops off the load. So a couple of reasons you might do something like this. One is maybe you live in a hurricane-prone area, right, or tornado alley or something, and you're worried about the equipment outside getting peppered with trees or something. Well, your indoor unit doesn't have that problem, so that's one reason. Another reason you might do it is maybe you're electrically limited to how much electrical capacity you can put into the site. You can't fully electrify your plant, but you want to electrify as much as you can to lower your carbon footprint. This gives you a good way of doing that. Maybe you also want just dual fuel sources, right? So maybe in extreme cold environments, right now they tend to shut off gas supplies and switch over to oil when it's really cold. As we move to electrification, our peak electrical demands are not going to be 6 to 9 o'clock during the summer. They're going to be, 2 in the morning on a freezing cold day because we're going to have electrified domestic HVAC. We're going to have electrified HVAC equipment. We're going to be charging our vehicles at night as well, right? So the load's going to shift. And so it might be useful to actually be able to turn on your gas-fired equipment at a certain point, depending on, utility rate demands. So there's several reasons why you might want to do this. All right, so let's take a look back at that 454B and CO2 plant comparison. So the CO2 equipment, like we said before, in this particular arrangement, we're at 3.44 COP. And again, this is at 44.6 dry bulb, 149 degree leaving water, 59 degree entering water, which is 90 degree delta T. We're only flowing 3 GPM, so this is a small capacity unit at 136 MBH. The MBH doesn't really matter in this comparison. We're just kind of looking at efficiencies. So our Galletti unit is a nominal 30-ton unit with a nominal 455 MBH worth of capacity. At the same ambient conditions and leaving water and entering water conditions, we're going to do a 10 degree per pass, right? So we're not going to do 90 degree in one pass. We're going to do 10 degrees, multiple passes. So we're running at 90 GPM here. Again, we're way more capacity. We're at 452 MBH. If we were to kind of scale it back, right, we could get closer, but we're still going to be way more flow than the CO2 piece equipment. So let's take a look at this. So if we have a system with no recirc, right, which is not a commercial system, most commercial systems do have recirc, then the CO2 unit would be running at its stated 3.44 COP. As soon as we add recirc, now we have a COP of 1 that needs to be weighted into the COP of the plant, right? So we've got our high COP for our CO2 plus our low COP of our electric resistance heat. And that 5% electric resistance heat knocks that 3.44 down to 3.3. And at 10%, we're below 3.2, right? And 3.2 is what we're operating at with the Galletti unit with the recirc, essentially. So what we see here is that Galletti becomes on parity with CO2 as soon as you have 10% recirc in the building. Now, when we get to 15%, right, we start to gain here a little bit. Most commercial buildings per day, right, have a domestic recirc load between about 30 and 60% of the overall load. Now, when we're in that range, we're about 20 to 60% higher overall plant capacity for a domestic hot water commercial system with an R454B unit compared to a CO2-based equipment. So if you're just looking at the rated performances, right, you would think, oh, CO2 is better. It is not, by and large, for most applications, right? And it's significantly not when you factor in the COP of 1 for that swing tank and what the real domestic hot water loads are in a building. All right. So I think I just said those points, got ahead of myself. All right, cool. So yep, that's the takeaway, right? Is that the Galletti unit is going to be 20 to 60% more efficient in a typical multifamily residential system with a domestic hot water recirc, which has a three-way valve, meaning the domestic recirc is running 24/7, okay? All right, so let's talk about global warming potential, because this one really throws people for a loop, right? So if you have a GWP of 1 for CO2, and then 454B has a GWP of 466. It's pretty easy to assume that the 466 is 466 times worse than carbon dioxide. But again, intuitions here are not good, so let's do some math. So this unit it's a nominal 30-ton unit. Usually you get about 2 pounds of refrigerant per ton. In this case, the charge is 62 pounds of 454B refrigerant, okay? So that's an equivalent of 28,892 pounds of carbon dioxide equivalent, which seems like a big, big number. It's 14 tons of carbon dioxide equivalent, right? Because a ton is 2,000 pounds. So if we were to release a full charge of refrigerant into the environment, it would be 14 tons equivalent of carbon dioxide, okay? So just keep that, well, you don't need to keep the number in mind. It's going to be on the screen, okay? So in New York City, they have this local law 97. And what they've done is they've put a number to the amount of tons carbon dioxide equivalent for a certain kW of draw of energy on the electrical grid. They also have a certain tons of carbon dioxide equivalent for certain NBH capacity of a gas-fired plant, okay? So obviously with gas, figuring out carbon's a bit more straightforward, but you got to be aware that, you know, we're not 100% carbon-free grids, right? So in the Northeast, about 46% of our electrical grid is fossil fuel based, okay? So even when you're consuming electricity, you're still consuming carbon, right? So the plant, and again, I'm not taking 100% of the full load plant capacity. I'm assuming that we're at about 35% of full load over the course of a year, which is pretty typical when you run the bin data, okay? So we're going to assume that we're running about 35% as a mean seasonal load. So that gives us 153,000 kW hours per year of energy that we're consuming. And if you run it through the electric, you know, kW tons per carbon dioxide per year, right? We end up with 44.3 tons of carbon dioxide equivalent just running our heat pump off the grid electrically, okay? So takeaway there is that the charge is equivalent to about 1/3 of just electrical operation throughout the year. So it's not insanely high. It's not nothing, right? It's a third of the year of operation. Now let's take that a little further, right? So again, we're not 466 times worse, right? But a couple things. So I think I had this reverse of what I wanted to say, but anyways, so the CO2 plant consumes 40% roughly, right? More energy with their swing tank included than a 454B unit. So on just a pure amp draw off of the grid, the CO2 based equipment, which looks better from a COP standpoint, right? When you factor in the system COP, is about 40% worse than a Galletti unit. So it's going to consume 40% more carbon, right? Now, refrigerant stays in the equipment, usually until the equipment fails, right? And it has to fail relatively catastrophically to lose the refrigerant. And so that is somewhere in the range of 15 years to 40 years of operation. Kind of depends on how well you maintain it, what's going on, you know, in the environment, whatever. But if you look at like a 30-year cycle, right, it's like an average. When you lose that charge, because you'll eventually lose the charge, right? Like I think it's like 3% of refrigerant actually gets recovered in the world. And most of it, you run it till you die, and it dies because you lose the charge, right? So, but that charge is equivalent to about 1% of its overall operation, right? So when you compare CO2 to 454B, it's not 466 times worse. In fact, it's 40% better. And the charge as a function, that 466, is only equivalent to about 1%, right, of the carbon footprint of the operation overall. So it's not a big deal, right? But it seems like a big deal when you're looking at 466 versus 1. So, all right. So what have we learned here, right? So basically, the 454B units are better for the environment compared to CO2 plants, somewhere in the range of 20% to 60% better, right? They cost a fraction to purchase, they cost a fraction to maintain. It's roughly about half the cost on both metrics. They're simpler to install, they're simpler to operate, and they're simpler to service compared to CO2 units. There's also a lot more techs available for, you know, traditional refrigerants and CO2. So basically, you know, it's the right choice for your air source heat pump equipment, whether you're worried about first cost, whether you're worried about the environment, whatever the consideration is for electrification, this is by far a better choice than the CO2 equivalents on the market. And with that, I guess I'll open up. I don't know if we're taking questions. So if we're not taking questions, I'll hand it back over to my colleagues in Italy. If we've got like some Q&A going, we could, you know, sit and, I guess, answer some questions.
Thank you, Bob. Thank you very much. Adam Hirschback here. Bob, that was an exceptional presentation on the pros and cons of 454B versus CO2. For those of you who have stayed on, this is the type of engineering work that Galletti North America does. It's what you can expect from our manufacturers' representatives in the local market. If you're currently working on a domestic hot water application and you're looking at the pros and cons of utilizing gas-fired equipment, going to electrify, looking at a hybrid plant, looking at the pros and cons of different refrigerants, the Galletti North America team is here to help you, to provide you with solutions for the entire system, from the heat pump to the gas-fired equipment to the circulators, heat exchangers, and everything in between. That's the value proposition that our company brings to you to support your project. So now I'd like to turn it over to Mattia, who will take us on a tour of the Galletti technical climatic chamber and introduce us to some of the newer equipment with R290 refrigerant, looking at advanced design and the future for North America. Mattia?
Welcome everybody. So for us, it's really an honor having you here. So thanks a lot for your presence and your time too. My name is Mattia, and I've been working in Galletti for 10 years now, more or less. I'm a product manager for chillers and heat pumps, And I followed the growth of 88 range with R410A and the future step, so with R454B too. Next to me, Filippo.
Yes, I'm Filippo, project leader from technical department, and I've been part of Galletti family since 2018.
So thanks, Filippo. Now we have a 3-minute clip focused on the Galletti lab test. So due to the large number of people connected, maybe you could have some problems, but don't worry, okay, about that, because for sure we can share the clip in a second time, but more important, we come back in 3 minutes here, okay? So, clip, please. Sta per finire. Perfect, so welcome again. I try to translate, to convert some numbers, okay? So we are talking about a facility that allows testing the unit starting from -4 Fahrenheit degrees of air temperature up to 122 Fahrenheit degrees, okay? So a very wide operating range. We can handle and keep under control not only the temperature of air and of course of water, but also the humidity in order to have the more realistic operating condition. Because what we want to, from this climatic chamber is to have a realistic behavior of the unit, simulating what can happen on field. So not have just a nominal performances, but realistic performances. We can also, for example, testing the unit considering the defrosting cycle, okay, and also glycol system, because we have 6 water connections, that means 3 water loops, in order to test air-to-water chillers and heat pumps, water-to-water, so water condensate, chillers and heat pumps, and also multi-purpose unit with 3 different plate exchanger. So we can test each kind of units and also with glycol inside the water loop. Not only, because as you can imagine, the big volume of the room, okay, allows to have very low airflow speed, okay, in order to doesn't affect the performances of the unit with a very high speed airflow, okay. Just to consider that big units has very large airflow rate, and if we would test the unit in a very small volume, this would translate in a very high speed, okay, of air that can affect the performances, the realistic performances. And we can also test, of course, not only R410A units, but also R454B or propane units. That means the climatic chamber is already approved for testing low flammable and high flammable refrigerant and units. The result of this investment is that Galletti can present on the market very reliable product, okay, also considering the possibility to test in very realistic conditions all the units in advance before the installation on field. On my left, for example, we have a R454B units, okay, this is a VLS unit, something very similar to the 88 unit you will have soon in your market with R454B. We use a scroll compressor, okay, heavy ice scroll compressor that allows the production of hot water up to 146 Fahrenheit degrees. This unit has a cooling capacity more or less of 45 tons. We have a wide offer on this range because we can cover, this is the smallest model, we can cover a cooling capacity starting from 45 tons up to 180 tons, more or less, okay, so a very wide range. Consider that R454B ranges are available with the Galletti brand in European market since 4 or 5 years ago. So we have already hundreds, thousands of units installed on field, okay. So it's something that will be new, okay, for US market, of course, but it's something that we are already tested and make reliable in Europe. The 88 R454B range is under testing in order to achieve the UL certification, of course, but for sure by the end of this year the range will be available for the US market. So this is our present solution and offer for European market, the solution of tomorrow for US market, but here we have also the future solution both for European and maybe, I hope, US market. So Filippo, tell us something about the propane units, please.
Yeah, sure. So as you may know, in Europe we recently have the review of F-gas regulation, which basically stated that every refrigerant gas with GWP higher than 150 will be banned in a space of 3 to 6 years. So we thought about a possible solution, and we came up to the conclusion that propane will be the gas which is the most suitable, at least for Europe, for the future. And propane, it's a highly flammable refrigerant, but it has also some interesting potentials. So, for example, it has a low GWP, just 3, and it has also a low density and excellent thermodynamic performances. So, as you can see here, you can see one of the first prototype we worked with. This is a 16 tons unit, and it's obviously a propane unit. It's equipped with a variable flow compressor. And as you can see, the refrigerant circuit is very clean, very simple. We worked a lot on that because we wanted to basically reduce the number of braising points, which can eventually lead to, let's say, some refrigerant leakage. And we also used state-of-art refrigerant components, especially in the heat exchangers. And to put into perspective, in this unit we have just 10 pounds of refrigerant, of propane. And if you have a look to something in R410A, for example, refrigerant gas, you can easily find something that is in the ballpark of 20 to 25 pounds of refrigerant inside. And finally, inside the unit, we have actually the refrigerant leak detector, which basically stops the unit if there is any kind of leakage, and triggers the extraction fans, which basically flushes all the gas out of the unit far from any source of ignition. And finally, as I mentioned before, propane has a lot of potential. The most important for us is the thermodynamic potential that it has, because this unit is able to produce hot water, up to 176 degrees Fahrenheit, which is very high. And I think that is something that is never done before with an electric heat pump. So this opens also the doors to a number of projects, such, for example, boiler replacement, but also process heating solution. So back to Mattia.
Thanks, Filippo. Very interesting. So we have the third unit here, so we can walk in the climatic chamber just to take a look. Okay, this is a MLE unit available in European market, another time with R454B refrigerant. The most important advantage that this unit and this range offers is the total heat recovery. That means we can produce cold water, warm water, and also both together using the total heat recovery. That allows very great performances, okay, because during the total heat recovery mode, the unit automatically switches off all the fans, okay, because we don't need to exchange heat with air, okay, and just recover all the condensing power, enabling the hot exchanger, okay. We can also move behind the climatic chamber in order to have a look also on all the piping system. That is something very interesting, and also it's really the core, the heart of the system. Here, okay, we have all the tank, the huge tank we use for testing the unit. So the hot water tank, the cold water tank, the source water tank in case of water condensed unit. We have all the PEMS, the glycol loop, and so on. So, as you can understand, it was a huge investment for Galletti, but really it was and it is the only possible way to have advantage on the market related to an advanced design solution. So, for the moment, and thanks again for your participation, your time. I leave the floor to Adam if you want to add something. Thanks again.
Thank you, Mattia. I'm going to hand this one over to my man, the creative thought scientist, Daryl Clark.
Thank you, Adam. Thank you, Mattia and Filippo, for that wonderful tour of the Galletti R&D lab. Folks, you have an opportunity to make a difference, to make a real change. There will be hundreds of millions, even close to billions of dollars spent over the next several years on heat pump technology. Your job is to make sure that some of that money flows through your fingertips and sticks. You have an opportunity to capitalize on what's happening now. Make a difference. Be in position to capitalize on this. We have the technology, we have the research. You've seen what Galletti has to offer. You've seen the investment that Galletti has made in research and technology, advanced innovation. Please, let me invite my colleagues, Enrico and Michele, to come in and join us as we close out. Thank you, guys. We have a tremendous, wonderful, wonderful team here, and we want you to make the investment like Galletti made. Invest in yourself and invest in the Galletti technology. Why? Because together we can make a difference, and together we win.